Thanks for inviting me. I'll talk about product-free sets in groups. And the main tool is going to be a hyperconductivity for global functions. Okay, so the main problem in extremal combinatorics, you are given a finite space of objects, and you want to understand how large can a subset of objects be, given some restriction on the set, on the objects in the set. And a set is extremal if it is the largest set that satisfies the restrictions. So for example, one such restriction that you can impose for a family is that it's intersecting. Okay, so if I take a family of sets, it's intersecting if the intersection of each two sets in F is non-empty. And this is the case where k is equal to 2, when you have graphs. And in general, you can talk about hypergraphs. And one example of an intersecting family, you can take the trivial intersecting family, the dictator. That you can take the family of all sets that contain a given element. And there is a family of sets. It corresponds to a Boolean function. So I have a corresponding Boolean function on the cube. And this dictator, it corresponds to the function fx equal to xi, which is known as the dictator. And the Erdős-Corrado theorem says that the dictators are the extremal intersecting families. And that's one of the themes of the Erdős-Corrado theorem, is that if you want to come up with the extremal families, you can take the first thing that comes to your mind. You don't have to think hard in order to determine the extremal ones. Okay. And this theorem opened a subfield of Erdős-Corrado type problems. When you have a set of an extremal problem, and you want to show that the extremal set for this extremal problem is a dictator. Okay, so this terminology stems from social choice. So you have a Boolean function, and you can think of 0 as pizza and 1 as ice cream. And you have a function that takes the votes and outputs whether with pizza or ice cream. And there are two types of Boolean functions that we can look at. We have the dictators that we determine what weight based on one voter. And there are also other important voting schemes that are juntas, that we decide the outcome of the election based on 3 votes. So we have these 3 people that determine the outcome of the vote. So, okay, and it turns out that juntas are not only important in social choice, they are also important in solving Erdős-Corrado type problem. So what does it mean for a family of sets to be a junta? It means that if we want to understand whether a set belongs to the family, we can throw away all of its elements and leave only its intersection with J, with the set of junta vertices. And what Irit and Daoud showed is that not only the largest intersecting family is a dictator, which is a one junta, but actually all the intersecting families have the structure of a junta. They showed that if I want to find an intersecting family, I can take so I can take the family. One example of an intersecting junta is to take the family of all sets that whose intersection with 1 up to 3 yeah, is at least 2. Yeah, so I can take the family of all sets whose intersects, take a majority on 3 elements, and this is an example of an intersecting junta. And what Irit and Daoud showed that this is the structure of all the intersecting families. If I want to take an intersecting family, I can start with an intersecting junta, remove elements from it, and add only a few elements outside of the junta, and this is the structure of all the intersecting families. And what Keller and I showed, we showed that you can actually use this this idea of using approximation by juntas to solve long-standing Erdős-Corrado type problems, and to use this junta structure in order to show that the extremal set is a dictator. So to bootstrap this rough junta structure into an exact dictatorial structure. Okay, so what do you have so far? We had extremal problems. So it's about how large can a set be given some restrictions. We had Erdős-Corrado theorem that says that the largest intersecting set is a dictator. And we talked about Erdős-Corrado type theorems, which are extremal problems that have dictators as extremal solutions. We talked about the junta method that helps solve such problems. Now we're going to talk about a totally different problem, which is the main thing that we're going to talk about, which is product-free sets. And this is a problem that comes from additive combinatorics, but actually it turns out that it's very related to Erdős-Corrado type problems, and it's actually a problem about dictators. Okay, so in group theory, we usually care about sets that are closed under multiplication. If we have a subset of a finite group, it's a subgroup if and only if it's closed under multiplication. And we're going to talk about the opposite question. What happens if for each 2 sets in the group, the product is outside of it? Okay. Okay, so yeah, so a set is product-free if and only if for each 2 elements in the set, the product is outside of the set. And the following problem was posed by Baba and Shosh in 1985, and asks what is the largest product-free set inside the group. And so can you solve the case where G is the symmetric group? What's the largest product-free set there? Yeah, okay. Yeah, so we can take the odd permutations. Okay, so if we take, yeah, so if sine of sigma is 1 and -1 and sine of tau is -1, so if we have 2 odd permutation, then the product is going to have sine 1. So the largest product-free set in the symmetric group. So the set of odd permutation is a product-free set, and it's also the largest product-free set, because if we take a subset of yeah, so if we have a subset of Sn and it's product-free, then A intersection with GA, this is empty for all G and A. Because the set is product-free, so it means that if we take an element in A, the intersection of A with G is going to be empty, and this means that the size of A can be at most 1/2. So this means that it's actually the largest product-free set. Yeah. Mm-hmm. Okay. Okay. So instead of asking this problem about Sn, which is quite easy, we ask this problem about we consider this problem about the alternating group, which was the original problem of Baba and Shosh. They conjecture that the largest product-free set in AN has density which is a constant, it's bounded away from 0, which turned out to be false. And it's also, Ben Green has a list of favorite 100 open problems, and that's problem number 4 in that list. And for us, the appeal that attracted us to this problem is that the conjectured extremal set for this problem is a dictator. So this is, even though this problem comes from additive combinatorics, it's actually a problem about dictators, and it's an Erdős-Corrado type problem. So, okay, so what are the dictators in the symmetric group? So, okay, so if you want to understand whether a permutation belongs to the dictator, we only need to check its value on one element. This means that 1 is the dictator. It decides whether a permutation belongs to the dictator or not. So the dictators are given by an index x and some set I, and you take all the permutations that send this x to the set I. These are the set of dictators. But when we define it like that, we get the dictators are not product free. And it turns out that it's easy to show that these dictators are not necessarily product free. But you can modify them a little bit, and you get the product free dictators. And what you do is you take the dictator and add an additional constraint. So you take all the permutations that send I to the set I, but also send the set I to the complement of I. And this set is product free. And Crane conjectured that this is the extremal product free set in the alternating group. Okay, so let's see why this set is product free. So suppose that sigma of I is in I. So sigma is in the dictator, so it sends I to I. And tau is in the dictator, so it sends I to I complement. And it means that sigma tau of I is in I complement. And we get that this set is not product free. Tau sigma, sorry. Yeah. And Crane conjectured that this is the extremal product free set in the alternating group. Okay. Now Gowers, he introduced a method from representation theory. So he introduced this notion of a quasi-random groups, which is a very influential notion in group theory that relates quasi-randomness of graphs with representation theory. So a group is said to be D quasi-random if every representation of dimension less than D is trivial. And what Gowers used the fact that this AN has this representation theoretic notion of quasi-randomness and deduced some upper bound on product-free sets. And this was his original motivation for introducing this notion of quasi-randomness. And Eberhard improved on it, and we showed this problem, solved this problem for sufficiently large n. And we showed that the extremal set is exactly of this form of the product-free dictator. So we gave an Erdős-Corrado type result in group theory or additive combinatorics. So what was Gowers' idea? So let's suppose, for simplicity, that A is equal to its inverse, and then we can talk about Cayley graphs. But everything works also without this hypothesis, but then we have to talk about directed Cayley graphs. And the idea was that the fact that A is product-free, it translates to the combinatorial fact that A is an independent set in the Cayley graph, where A is the set of generators. So A plays two roles here. It plays one role as a set of generator, but it also plays a role of a set of vertices. And as a set of vertices, it's an independent set. And what Gowers showed is that this representation theoretic notion, and it's based on some ideas from Sarnak and Chu, that this representation theoretic notion, it implies this quasi-randomness of graphs, that every Cayley graph, that every large Cayley graph for every large set A, the number of edges between two large sets is exactly as it would be in a random graph of the same density. So this representation theoretic notion implies that graphs are quasi-randoms. And in particular, if you have a large set, then it can't be independent because two sets must contain as many edges as a random graph of the same density. And in particular, they must contain some edges. Okay. Let's talk briefly about Gauer's idea. The idea is quite simple, actually. You can take the operator that corresponds to the random walk, which is the expectation over A in A of FAA, TF of X. And it turns out that if you take T squared and take the trace of it, then this is, you can compute this. What's the trace of T squared? It's like taking two steps of the random walk and asking what's the probability that you return to the same spot, and then multiplying by n factorial. So it's n factorial over the size of A, but on the other hand, it's equal to the sum over eigenvalues of the multiplicity of the eigenvalue times the eigenvalue squared. And this in particular implies that lambda is at most n factorial times the size of A. Yeah, lambda squared is at most that times m over m lambda. So large m lambda implies small lambda. So this is the relation. Once you have large multiplicity for an eigenvalue, then you get that this eigenvalue is small. And once you have small eigenvalues, you get that your graph is quasi-random. Now, how do you get this large multiplicity? This follows from representation theory. So representation theory gives you large multiplicity because this operator, it's defined by multiplication from the left, so it's symmetric with respect to multiplication from the right. And then you get that this operator satisfies a certain symmetry that implies that all the multiplicities must be large. And then once you have large multiplicities, you have small eigenvalues. And once you have small eigenvalues, you have a pseudo-random graph. Okay. That was roughly Gauer's proof. But it turns out that there are other ways to show mixing, to show that, and we basically use tools from Boolean functions. So one of them is hypercontractivity. And if you look at this proof, it only uses L2. So the proof uses L2 norms. And it turns out that you can use LP norms to get something much better. And when you use L2 norms, you only make weak use of the Booleanity of the set of generators. You don't use the fact that it's a set a lot. But when you use LP norms, you can make much more use of the fact that you have a set of generators rather than an arbitrary function. Okay, so that was our idea, to try to use hypercontractivity and generalize it from the Boolean cube to the symmetric group. But it turns out that if you try to generalize it in a straightforward way and prove hypercontractivity for all functions, then you get a result that's not very effective. And the reason is that you have these dictators that are very small. So if you look at the Boolean cube, you have the function fx equal to xi. This has expectation 1/2. On the other hand, if you take, if on permutations, you can take the function that's the analog function that outputs 1 when the permutation sends 1 to 1. This is expectation 1/n. And that's the reason why everything fails for the symmetric group. So we had to come up with a notion of hypercontractivity for global functions that's inspired by the breakthroughs on the 2-to-2 games conjecture, the proof there. And it turns out that you can use it for various other problems, and that we're not going to talk about, but it turns out that it has various other applications. Okay. So are there any questions so far? It's n quasi-random. Yeah, it's not very, it's only logarithmic in the size of the group, so it's not very powerful. But so you get d to the third, where d is the quasi-randomness parameter, and but our methods actually allow you to go much beyond that, and so we can actually show that if your set has size which is at least, if its density is at least e to the minus n to the third, then it already implies structure. So we can actually improve exponentially on pure representation theoretic arguments by letting analysis get into the picture and use hypercontractivity to improve on these results. Are there any more questions? Okay, so I don't assume that you know what hypercontractivity is. I'm now going to explain what it is. And it's about a noise operator on the Boolean cube. So you can imagine the Boolean cube as this paddle, and you have this smoothing operator that takes a vertex in the cube and averages over a small set near x. So this idea of using a hypercontractivity, it originated in differential geometry when you have these smoothing operators, and once you have, and the smoothing operator is defined by taking expectation over a small ball around x. And in the cube, it's defined in the same way. But you have to understand what does it mean to be close to some x. And the way to define it is by via this noisy random walk, where you start with some x in the cube, and you get a noisy version of it by remembering each coordinate of x with probability rho, and forgetting it and resampling it with probability 1 minus rho. And then you get some vector y that's close to the original vector x, and you get a distribution over these y's. And then you can define this noise operator, which is defined by taking expectation over these y's. So you take expectation over y that's close to x. So you have this noisy process that starts with x and gives you some y in that ball, and you take expectations. Okay. One of the things that was proved for this operator is a theorem by Kahnke-Lyon linear, which is the small set expansion theorem. It tells you that if you have a small set and you take one step of the random walk, then you are going to leave the set with high probability. This means that if you take small set inside the cube, most of their elements are near the boundary. So if you take a random element and you move it even a little bit, you're going to get outside of the set. So small set expansion tells you that if you take a small set and you take a random element of the set and you take one step of the random walk, then you are going to leave the set with high probability. So that for every small set, for every small set, you're going to leave it with high probability. So it means that for every small set, most of its elements are near the boundary. Okay. And formally, we said that the set is small if its density is little over 1. And the small set expansion theorem tells you that if you take one step of the random walk, you're going to leave the set with high probability. That's a theorem by Kain-Kalai and Lineal that that introduced this idea of using hypercontractivity for Boolean functions. Rho is fixed, exactly, yeah. Okay. And hypercontractivity, which is the tool that they use to prove their small set expansion theorem, it's called hypercontractivity because it's about contraction of operators. So you can talk about the L2 balls, the L2 unit ball of all function whose two norm is at most 1. And you have the L4 ball, and F2 squared, let's say, is the expectation of F squared. And you have the L4 ball of all functions whose 4 norm is at most 1. And it turns out that if you take a probability space, then the L4 unit ball is always contained in the L2 unit ball. But if you apply the noise operator, then it's going to take this big unit ball and send it into the smaller unit ball. So it's not just a contraction. Contraction will tell you that you send an LP ball to itself. It's a hypercontraction that tells you that you send big balls into small balls. And that's the hypercontractivity theorem. In the special case where the norms are 4 and 2, there is a general version for general norms. And it tells you that you send the big L2 ball into the small L4 ball. In formula, it means that T F, the 4 norm of T F is at most the 2 norm of F for all functions F. Are there any questions about hypercontractivity? Okay, so how do we think about hypercontractivity in more intuitive terms? So we can think about two behaviors of random variables. One is the smooth behavior, when the 4 norm is within a constant of the 2 norm, like a Gaussian random variable or the dictator, the 4 norms is within a constant of the 2 norm. But you also have this picky behavior, where you take the value, let's say root n, with probability 1 over n, then you get that the 2 norm is 1, but the 4 norm is much larger. The 4 norm to the 4 is going to be n. So the 4 norm is going to be n to the 1/4. And it means that there is a big difference in behavior between, so there is this smooth behavior and there is this picky behavior, these two very different behaviors. And if you look at indicators of small sets, they have the picky behavior. So let's say that F is the indicator of a set. And the size of A is alpha times 2 to the n, and alpha is little of 1. Then you get that the 2 norm is little o of the 4 norm of F. This is exactly as the picky behavior, where you get 1 with a very small probability and 0 otherwise. And it turns out that hypercontractivity it's a smoothing operator, and it sort of rules out this behavior for low degree polynomials. So let's talk about that. So we have the Fourier characters over the Boolean cube. So every function on the cube, we can write it as a multilinear polynomial. So if we have f from the cube to the real numbers, we can write it f as a sum of f at s times the product of I in S of xi. That's the full expansion of f. And this expansion is, and this is the way to write f as a multilinear polynomial when the inputs are -1 and 1 valued, unlike Shahar's talk. But this full expansion, it allows you to give a notion for a degree of a function. So the degree of the function is t if it's the degree of f as a multilinear polynomial. And it turns out that hypercontractivity implies that that these low degree functions, they have the smooth behavior. So if we look at degree 1 functions, we have the dictators that have the smooth behaviors. And we also have Gaussian random variables. When we take the sum of the xi and normalize, we get Gaussian random variables, and their 4 norm is within a constant of the 2 norm. And hypercontractivity, it allows you to show that so it allows you to show that low degree functions are smooth. And on the other hand, indicators of small set, they have the opposite behavior, the peaky behavior. And okay, and let's talk and let's show the proof. In the case where f is a homogeneous polynomial, so here f. So let's say that f is a homogeneous polynomial, so it's the sum over s of size b of f at s chi s. Then we get that T rho f is rho to the d times f. And then when we apply hypercontractivity, we get that T rho f 4 norm. This is at most the 2 norm of f. And this is equal to rho to the d times the 4 norm of f. And yeah, so you can use this diagonalization of the noise operator to show that low degree functions, these homogeneous functions, are the eigenfunctions for this operator, and then deduce that low degree functions have a smooth behavior. And this noise operator, it also kills the high degrees. It shows that this rho to the s becomes smaller and smaller as s gets larger. So it kills the high degrees. And then if you start with a small set, so the noise operator already kills the high degrees. And you sort of can use this difference in behaviors between small sets and low degree functions to say that small sets are not correlated with the low degree function and have all the Fourier mass on the high degrees. And that's how you prove small set expansion. So the idea is to use this dichotomy to show that, so the noise operator kills the high degrees and the smoothness kills the low degrees inside small sets. Okay, and this leads us to the following 3 equivalent ways of thinking about hypercontractivity. So we have the hypercontractivity theorem. We have one combinatorial which says that you send the big L2 ball into the small L4 ball. You have small set expansion that says that if you start with a small set, then you are going to leave it with high probability. And you have this smoothness of low degree functions, which tells you that if you have a low degree function, its 4 norm is within a constant of the 2 norm. And these are all similar ways of thinking about hypercontractivity. And we want to generalize it to the symmetric group. And one toy model for the symmetric group is m to the n, or n to the n. We can think of Sn as a subset of n to the n. We can think of Sn as vectors that have all their coordinates distinct inside n to the n. So this is like a toy product model. And it turns out that if you try to generalize the theory from the Boolean cube to the symmetric group, there are lots of things that go wrong, namely the small dictators, and you need to come up with something else to overcome this. Okay. So what are the dictators in all the domains, in all the other domains? So we have the Boolean cube, where we have the function fx equal to xi. if you want to generalize it to the symmetric group, as we mentioned, you take f of sigma to be 1 when sigma sends I to j. And it turns out that if you want to talk about hypercontractivity in the symmetric group, it turns out that all you need to know is the definition of dictators. So, so there is some, so there is the greedy composition inside Sn, and you can refine it to get the representation theoretic decomposition. And this is a coarser decomposition, which and it's defined as follows. All you need to know in order to define the degree decomposition, it's much more elementary. You only need to know the notion of dictators. And okay, so what is the notion of low degree functions? So we need the dictators to be of degree 1, and you need products of d dictators to be of degree d. And that's how, and you define a function to be of degree d if it's a linear combinations of products of d dictators. So once you know what the dictators are, you know what the low degree functions are, and you can ask whether hypercontractivity is true or not. But it turns out that it's not true. So it's not true not in Sn and also not in the toy model. And the reason is that in both of them we have these small dictators and dictators and small sets are always counterexamples to hypercontractivity because they have this peaky distribution. And but in the Boolean cube, dictators are not small. Their expectation is large. Their density is large. On the other hand, in the symmetric group, dictators can have density 1 over n. And, it turns out that they not only ruin small set expansion, but actually small dictators, they ruin everything. And okay, so what did we have so far? So we talked about the fact that many spaces have notions of dictators. And once you know what dictators are, you can define what the low degree functions are. They are the linear combinations of products of the dictators. And then we can ask whether low degree functions are smooth, whether the form of a low degree function is at most a constant times its true norm. And one obvious obstruction is if there already exists a dictator that's sparse. That means that there exists a function of degree 1 without this property. And the idea is, and our solution was to filter out the dictators. Instead of proving hypercontractivity for all functions, it's not very useful. We just filter out the dictators and prove hypercontractivity only for the functions that don't have dictatorial structure. Okay, so how do we generalize the noise operator to other spaces? So it's actually quite straightforward. In the multicube in m to the n, you do the same thing. Each coordinate you can forget it with probability 1 minus rho and remember it with probability rho. And the coordinates that you forget, you resample them uniformly at random. And again, you can define this noise operator by taking expectation over a small neighborhood around each x. So this way, using this noisy process, you get a vector that's close to the original x, and you take expectation and get this averaging smoothing operator. Okay, and it turns out that sparse dictators, they don't only ruin the smoothness of low degree functions, they also kill small set expansions. And if you take the dictator here and you take one step of the random walk, there is a probability rho that the first coordinate is still 1. So even though A is a very small set, it has density 1 over m. When you take one step of the random walk, you stay in the set with a constant probability. So that's a counterexample to small set expansion. And it turns out that you can make a calculation and show that they also they don't have a hypercontractivity. They're also a counterexample for hypercontractivity. So you really need to filter them out in order to get some result. And then there are these ways to deal with the sparse dictators. So one way to do it is to decrease the noise rate and allow rho to depend on m or on n, like and prove hypercontractivity when rho is 1 over root n. One other way to deal with this fact is to prove reverse hypercontractivity, which is a very common tool in Markov chains, but it's not sufficient for our purposes. It's very good when you apply some operator multiple times. It's good for continuous time. And here we're talking in discrete time. And what we use is hypercontractivity for global functions, and basically to filter out the bad dictators and prove hypercontractivity for all the rest of the functions. Okay, so in order to set a result, we have to define what the restrictions are. So I'll write that down. This definition here is a bit messy. So basically, you have a function, and you can restrict it inside the dictator. So if you can look at the first coordinate and put x, let's say, in the first coordinate, and get a function on the rest of the coordinate. By letting f1 go to x of y be f of xy. Okay. And more generally, you can take a set of coordinates and plug in x in those coordinates and get a function on the rest of the coordinates. And our definition of global tells us that when we take these restrictions, we don't increase the 2 norm of the function by too much. Okay, so the notion says that f is epsilon global if the 2 norm of f when we so if it in particular says that the 2 norm of f is at most epsilon, because we can take S to be the empty set, but it also means that its 2 norm inside each dictator is at most 100 times epsilon, and it tells you that if you take the intersection of 2 dictators, the 2 norm inside them should be at most 100 squared times epsilon, and so on. And the best epsilon you can take is the 2 norm of f, because you can in particular take the empty set. And the trivial epsilon to take is the infinity norm. If you take epsilon to be the infinity norm, then it holds for all functions. And it turns out that in the Boolean cube, you can actually always take epsilon to be the 2 norm of f, and it's true for all functions. And that's why this notion of globalness only comes up when you move to other settings. In the Boolean cube, every function is 2 norm global. Okay, so f is not global if it has a density bump in some intersection of dictators. And the dictators are the ultimate example of functions that are not global. But if you want an example of sets that are global, you can take a random set and it will be global. So this is like you can think of it as a pseudo-randomness notion. But it's also, you can think about it as a cube-like notion. It means that if your function behaves like a function on the cube, then it's global. So you can take, if f of x depends only on whether xi is even or odd, so we can encode the function on the Boolean cube as a function on the larger multi-cube by letting f of x by caring only on whether each coordinate of the input is even or odd. And these functions are going to automatically be global. And what we proved that once we have a global function on the multi-cube, you can recover all the results from the Boolean cube. So if you have the optimal epsilon, which is the 2 norm of f, you recover hypercontractivity, and you get a constant noise rate, and you still get hypercontractivity, that T rho f, the 4 norm of T rho f is at most the 2 norm of f. We also get this smoothness of low degree function. We get that if f is a low degree function, then its 4 norm is within a constant of the 2 norm. And we also get small set expansion, and here we don't need epsilon to be the best epsilon in order for us to get small set expansion. You only need epsilon to be little o of the infinity norm of f. So you just need epsilon to be to beat the worst example, the infinity norm of f, and you already get small set expansion. And later we generalized it from the cube. We generalized it to the symmetric group, which ultimately was what allowed us to prove the theorem. And okay, the summary of my talk is there are two things that I want you to take with you. So one thing is that the extremal product free sets in the alternating groups are dictators. So Erdős-Corrado type problems don't appear only in extremal combinatorics, but they actually appear also for problems in the symmetric group. And the second thing is that hypercontractivity for global function is a very powerful tool when you have sparse dictators and you have to filter out the bad dictators and prove hypercontractivity for the rest of the functions. And yeah, so that's the main themes, and there are like future works about generalizing it to Lie groups and the symmetric group that I'm not going to talk about. So thanks.
Any connection, strong or weak, between the representation theory of the group and the nature of hypercontractivity that you?
Yeah. There is a very strong connection. So the connection is that okay, yeah, that's a very good question. Okay, yeah. So if you look at these low degree functions, this is a representation of Sn, and it can be decomposed into isotypical components. And it turns out that the connection between these two problems is that we said that high multiplicity implies small eigenvalue. Okay, but instead of using the smallest multiplicity, which is what you do in quasi-randomness, you just look at the smallest dimension. You can use the fact that it turns out so that high degree, it corresponds to high multiplicity, to even higher multiplicity. So you can you have a decomposition of the functions on the symmetric group into an orthogonal decomposition into a direct sum of spaces v equal to d, where v equal to d are functions that are of degree d and orthogonal to all functions of degree d minus 1. And in this space, the smallest dimensions are much higher. They are not n like it is for the alternating group, but they are n to the d. And the higher the degree is, the higher the multiplicity is. And yeah, so high degree implies high multiplicity. And what we're good at doing in Boolean function is showing that small sets are far from low degree functions. So if you decompose an indicator of a small set according to this decomposition, it's going to have all its mass on the high degrees where the multiplicities are much higher. And then you can use the representation theory of the symmetric group to get much better results. And It's not true for all small sets actually, because dictators are counterexamples, but it's true for the small global sets, and they are far from the low degree functions, and then you can get and then you get it effectively, even though the quasi-randomness in AN, so the quasi-randomness is the smallest dimension of an irreducible representation, even though it's bad in the alternating group, you get it effectively. It's actually not that bad, because small sets, small global sets at least, they are concentrated on the high multiplicity and on the high multiplicities, and you can sort of recover quasi-randomness for these sets, the good quasi-randomness, which is almost polynomial in the size of the group. Yeah. So the multiplicity is the high multiplicity. It's because the eigenspaces are representation of Sn, and therefore their dimension has to be large. Yeah, and the V equal to D in terms of Young tableaus. This corresponds to the Young tableaus with n minus D boxes in the first row, and D stuff everywhere else. So here we have n minus D, and here we have other stuff. N minus D in the first rows, and D stuff below the first row. Yeah.